Hey students, welcome to lecture number 13 of multiple zeta values and modular forms. So last time we talked about period polynomials and their connection to the formal double zeta space, and more precisely we showed that there's a map of modular forms to the space of polynomials given by these period polynomials, and the space of period polynomials are isomorphic to a certain subspace of this formal double zeta space. So we didn't really prove these two theorems we had there, but you can find the details in the lecture notes and also in the notes coming from the live lectures in Zoom. So today we want to start with section number 5 and talk about multiple Eisenstein series, which somehow can be seen as a mix of the definition of Eisenstein series and the definition of multiple zeta values. And the goal today is to calculate the Fourier expansion. So, but first, recall the classical Eisenstein series. So these we defined for even k, greater or equal to 4 even. We defined them as this sum here. We denoted it by gk, and this was 1/2 given of this sum here, where we sum over all lattice points which are non-zero, and we sum up this term 1 over m tau plus n to the k. And tau here was an element in the upper half plane. And then we said, we didn't prove it, but we will do it today, that these have a Fourier expansion of the following form, where the constant term is given by the Riemann zeta value zeta k, and the remaining term is given by this generating series of the divisor sums. And here this q is e to the 2 pi I tau. And in the whole talk, q will always be e to the 2 pi I tau. So the goal today is to define a multiple version of these in such a way that they also have a Fourier expansion, and the constant term will be given by multiple zeta values. And then of course the big question is, what is this term here? And with the notation we had before, this is our Q series gk, but here with some factor in front. So we will see that these multiple Eisenstein series and the Fourier expansion will also contain these multiple version of these g, but it will not be just the multiple zeta value and the multiple version of g. There will also be mixed terms of multiple zeta values and these Q series g. So but first let's recall how we can actually calculate this Fourier expansion here. So to do this, so here's again the definition. What we do is we split this summation here into two terms. So here we sum over all lattice points m and n, which are not both 0. So but we can consider the case when m equals 0 and when m is not 0. And so if m equals 0, then we don't have this term here, and we sum over all non-zero integers n, and we get this sum here. And now we use that k is even, and therefore we can restrict to the case when n is positive, and this factor 1/2 we can then ignore because we have twice the part when n is positive. So this will give exactly zeta k. So this comes from this part here. And also because k is even, we can in this case here, when m is not 0, we can also restrict to the case where m is positive. Of course, we can also multiply this here by -1 to get it in the upper half plane. And then we also lose this factor 1/2 here. But you see, if you multiply this here by -1, then because we sum over all integers n, we will get twice this sum here. And then to evaluate this sum here, we use the following formula, the so-called Lipschitz summation formula, which states that for k greater or equal to 2, this term here, the sum over all integers n of 1 over tau plus n to the k, can be written as this Fourier series here. So therefore, plugging this into this formula here, we get, so first of all we have this factor here, minus 2 pi I to the k. And then we have the sum over m. And now for this term here, we use this formula here. But because we have m tau here and not just tau, we have here q to the m times d. So here we have the inner sum, d goes from 1 to infinity, d to the k minus 1. but here it's q to the m times d. And here you see this is exactly the sum we had before, because now what is the coefficient of q to the n? Where the coefficient of q to the n is exactly the sum of all divisors of this n. So here we have exactly sigma k minus 1 n. So the Fourier expansion follows directly from this Lipschitz summation formula. And the proof of this Lipschitz summation formula, or the proof sketch, is, so there are several ways to prove this, but one way is to consider the cotangent, which we also considered before when we talked about this Euler formula. And this cotangent can be written in two ways. So the cotangent also has a Fourier expansion like this. And the cotangent also has a partial fraction decomposition. So we can write this as 1 over, this is not a z, this is a tau. So this is then 1 over tau plus, and here we take the sum, n goes from 1 to infinity. So in this formula we already used when we proved this Euler formula. And now this formula follows from this one here by just taking the k minus 1th derivative. Then you will see if you take the k minus 1th derivative of this, you get this term here with some factorial, and if you take the k minus 1th derivative of this, you get this part here, and then in total we get this formula here. Okay. And so in total we get that, well, this is just a recall, that the Eisenstein series has this Fourier expansion like this. So we get, by the Lipschitz summation formula, we get this, but this is just the sum of the divisors here. And this can be written as zeta plus some power of pi times our Q series G, because this here was exactly the definition of this small gk. And now we want to generalize this, so we want to define a multiple version of this. So in the case of so how did we define multiple zeta values? They were a multiple version of the Riemann zeta value, and the Riemann zeta value was defined. Well, what was the definition of the Riemann zeta value? This was, maybe let's say n. The sum over all positive integers of 1 over n to the k. And we see here that this comes from here, but here we don't really take the sum over all positive integers, we take the sum over all integers which are non-zero. And this comes from the fact that we take here the sum over all lattice points which are non-zero. So what we want to do is we want to introduce the notion of a positive lattice point. And then instead of taking the sum over all lattice points, we will define the single Eisenstein series as a sum over all positive lattice points. And then it's quite clear how we can generalize this to a multiple version, because then we can just say we take the sum over all ordered lattice points. Because the way from here to the definition of multiple zeta values was just, well, instead of saying I take the sum over all positive integers, I take the sum over all ordered positive integers of 1 over m1 k1 up to mr kr. And we will do the similar thing here. So instead of saying we take the sum over all lattice points, we take the sum over all positive lattice points, and then we take the multiple version will then be defined in a similar way like this. Okay, so let's define this order. So one should also say, so this everything I say today is based on a work of Gangan and Zagi, where they first introduced the notion of double Eisenstein series in the work which you can find in the lecture notes. And there they also introduced this order here. So what is the definition? So tau is an element in the upper half plane, and we now want to say what it means that one lattice point is larger than another lattice point. So let lambda 1 and lambda 2 be two lattice points. Then we say lambda 1 is greater than lambda 2 if lambda 1 minus lambda 2 is in P. whereby P, which we call the set of positive lattice points, we define it as the following subset. So the P is given by all lattice points which are in the upper half plane and all lattice points which are on the positive real axis. So for example here you see in the picture, if tau would be I, then these are exactly, so the set U are all lattice points in the upper half plane, and the set R are all lattice points on the positive real axis. And so another way to phrase this here would mean that so a lattice point M1 tau plus N1, so this is larger than M2 tau plus N2. So whenever, for example, so either M1 is greater than M2, so this means the difference of these two lattice points is in the upper half plane, or if they are the same, then the N1 should be larger than N2. So for example here, this lattice point lambda 1, this is larger than this point here because it's above lambda 2. But also this point here is also larger than lambda 2. But also everything on the right of lambda 2 is larger than lambda 2, and more generally everything here in this space here is larger than lambda 2. So a lattice point is larger than another lattice point if it's above or if it's on the right, and on the same level when it's on the right. Okay, and also notice that the set P, so if I combine this with the negative set P, so if I multiply these with -1, then I get exactly the remaining part here, so I get everything except for 0. So this here is minus P. So therefore, the union of P and minus P is exactly the whole lattice without 0. Therefore, we can rewrite our definition here of Eisenstein series. So here we took the sum over all lattice points with a factor 1/2. So but this will now be the same as 1/2 taking all lattice points in P union minus P, 1 over lambda to the k. But now because we consider just the case when k is even, we can again, then if I evaluate lambda to the k for a lattice point in minus p, it's the same as the lambda for being in p. So this is the same as just taking the set of all lambdas in p of 1 over lambda k. And being in p just means it's positive. So in other words, I could also rewrite this as saying that I take this sum over all lattice points which are larger than the lattice point here, 0. So in here, we see that this now looks more similar to the definition of the Riemann zeta value. And also notice that with this, if k is odd, then this is not 0 anymore. In this case here, if k is odd, then if k is greater or equal to 3, this sum converges, but because each point cancels out with its negative point, this sum vanishes in the case k equals odd. But this sum here, we could take this now as a new definition of gk. So this is a new definition. But now, for all k greater or equal to 3, and then this vanishes, this doesn't vanish anymore for odd k's, but we also see that this calculation here of the Fourier expansion, this still works with the same argument, because we can again consider the case when m equals 0 and when m is positive, and we can use exactly the same formula. So we get again exactly that this is zeta k plus, and then this term 2 pi I to the k of gk. And this is null for all k. And therefore, because we are interested in zeta values and we are also interested in odd zeta values, we will use this definition now for gk for all k greater or equal to 3. Of course, for odd case, this is not a modular form anymore. But also, using this, it's clear now how we can define the multiple version of these guys. And this is the following definition. So these are now our main objects here. So the multiple Eisenstein series are defined for k1 greater or equal to 3 and k2 up to kr greater or equal to 2. So this is for convergence reasons. And then we define the multiple Eisenstein series gk1 up to kr as this sum here, where we take now the sum over all ordered lattice points lambda 1 up to lambda r. So these lambda i's are in the lattice z tau plus z. And then we take 1 over lambda to the k1 up to lambda r to the kr. So this is, if you would replace the lambdas by natural numbers, then this is exactly the definition of multiple zeta values. And again, the weight will be the sum of these k's and r's, the depths. And with this definition here, it's also clear that they satisfy the Staffel product formula in the cases when they are defined, because it uses the same argument as before. So for example, if I multiply G3 with G4, then I can again use this argument. So here I take the sum over all lambda 1's positive and here over lambda 2 positive. And then I can split it up into the part where lambda 1 is greater than lambda 2. So this will give G3, 4. And then I have the term where lambda 2 is greater than lambda 1. So here I have G4, 3. Plus when they are the same. So this is G5. And yeah. But so the definition is now a little bit more restricted. But one thing we can do is we can also allow this k1 to be 2. So in this case, this sum is not absolutely convergent, but it's conditionally convergent. So we can choose an order of summation to define this, and this we will do as follows. So first, so this was already done by Eisenstein, for example, for the case G2. So the idea is to introduce the following order of summation. We will take first the sum over on the horizontal line, so these ends, and then we take the sum over the vertical line. So and then one can check where inside here we can use again the Lipschitz formula, and here we get the same as with the same argument as before. We get a zeta 2. So, but this sum is not absolutely convergent. So in this case, this is not a modular form, but this this limit here exists, and this gives exactly zeta 2 and g hat 2. Where I forgot to introduce here what I mean by g hat. So g hat just means that we introduce this this factor minus 2 pi I to this g2. And here, if you would interchange these two limits, then you would actually get something different, which will maybe, so if you interchange this here, if you take first the summation in the vertical axis and then the horizontal axis, then you would get a factor of, I think, 2 pi I over tau. But this is just a comment, so we will use this summation here. So in general, we will now allow also, so k1 up to kr greater or equal to 2. So one can check that these multiple Eisenstein series are also conditionally convergent in this case, and we will also use this summation here. So we will first sum in the horizontal axis and then in the vertical, and here this notation zn just means I take all integers n where the absolute value of n is smaller than n. So here this is just a sublattice, the points which are in this rectangle here. So this is actually a finite sum, and then we take first the limit n, so we first send these two to infinity, and then afterwards we send this m to infinity. And this sum makes sense for all k1 up to kr greater or equal to 2. Okay. So now, what we want to do in the rest of the lecture is to calculate the Fourier expansion of these guys. So, yeah, so recall in depth 1, the Fourier expansion was given by this. And now I want to introduce this notation here, which I did in the depth 1 case before. So we will see that we will always have these g together with this factor minus 2 pi I to the k, and therefore we will introduce this g hat, which just means we have this our Q series g, k1 up to kr, where we have this factor minus 2 pi I to the sum of these k's. Okay, and then the statement is as follows. So these multiple Eisenstein series have a Fourier expansion, and more precisely they can be written as a multiple zeta linear combination of these g hats. So more precisely, one can write down explicit coefficients, alpha, which are rational numbers, such that this multiple Eisenstein series, so as a constant term, it has zeta k1 up to kr, and here at the end it has this g hat k1 to kr, and in between we have a mix of multiple zeta values and g hats. And here one sees that this is a multiple zeta values of depth j, and this j is greater or equal to 1 and strictly smaller than r. And here this the depth of this g is also greater or equal to 1 and strictly smaller than r. So the only depth r terms in this expansion here is given by this multiple zeta value and by this g hat, and in between we have a mix of smaller depths multiple zeta values and smaller depths g hats, and they have some rational factors here. So let's maybe look at an explicit example. So we will see how to calculate the following. So the Fourier expansion of the multiple Eisenstein series G322 has the constant term zeta 322. Then here we have some depth 1 g hat. Here, for example, g hat 2 has some double zeta values here and some rational numbers. So these are the alphas. And also here some alpha and some double zeta value and g hat. And also notice that the sum of these L is always exactly k, which is the total weight. So in some sense everything here is homogeneous in weight. And here we have some double g hats and some single zeta values and some alphas. And in the end we have again this g hat of exactly this index here. Okay, so now the question is, how do we calculate this expansion here? So in other words, how can we derive these coefficients alpha? And the idea will be similar to the classical case. So here we split it up into two cases, and in general we will split it up into 2 to the r different cases. And then we will also at the end use this Lipschitz summation formula. But we will need to generalize this term, this cotangent appearing in this Lipschitz summation formula a little bit. And this will be done as follows. So for this we introduce the following functions, the so-called multitangent functions. So these functions were first considered by Jean Ricard, and then by one of his students, Olivier Bouillot, in his thesis. He studied these functions in detail, and you can find the references in the lecture notes. So for integers k1 up to kr greater or equal to 2, and some complex number x, which is not an integer, and we define the multitangent function of depth r as psi k1 to kr of x, and this will be given by this ordered sum here. But notice that here we take all integers, so they don't need to be greater or equal to 0. It's just that we have ordered integers, which can also be negative, and then we take the sum over 1 over x plus n1 to the k1 up to x plus nr to the kr. And in the depths r1 case, we call them a monotangent function. And also, so what is this in depths 1? So if we write down the definition in depths 1, so here we just have where there's just one integer, so it's not ordered, so it's just the sum over all integer n. And we take 1 over x plus n to the k. And here notice this is exactly the left-hand side of the Lipschitz summation formula, where we showed that this has a Fourier expansion of the form minus 2 pi I to the k minus 1 factorial d to the k minus 1 q to the d. Well, maybe here then I should write tau. And so the main ingredient now is, or the main result we need is that these multitangent functions can actually always be written in terms of these monotangent functions, and with coefficients given by multiple zeta values. And this is the statement of the following theorem due to Olivier Bouillot. So this is the so-called reduction of multitangent into monotangent functions. So in the case when k1 up to kr squared equal to 2, then the multitangent function psi k1 up to kr can always be written as an explicit linear combination of monotangent functions. So here psi j, so this is now a single j, which runs from 2 to k, where these coefficients cj, k1 to kr are given by some multiple zeta values of weight k minus j. So here this is also again in some sense homogeneous, because this here has weight j, and this here is a linear combination of multi-zetas of weight k minus j. And k is the sum of these k's. And so the proof idea, we will do one example in a second, is based on a partial fraction decomposition. But also one main point here is that this sum here starts at 2 and not at 1. And for this, an explicit relation among multiple zeta values is necessary. But this will be one important point, because later we will have these multitangent function, and then we want to write them in terms of these monotangent functions. So let's do one explicit example of this reduction. So let's consider the multitangent function psi 3, 2. So by the definition, it's given by this sum here, where we take the sum over all ordered integers, which can also be negative. And now for this inner term here, we can do a partial fraction decomposition, which with respect to x, which will give this term here. And now, first of all, we see that that these two terms here, so if we take the sum over all n1 and n2, then these two terms are actually the same up to a minus sign here. Because I could rewrite this sum here, so n1 minus n2, so n1 is greater than n2, so I could rename this to say this is n1 prime, and this is maybe n2. So then instead of taking the ordered sum of n1 is greater than n2, I could rewrite it as a sum where n1 prime is positive and n2 is some arbitrary integer. And also here I could call this n1 prime, and also here this I could call, well, it's already called n2. And then you see that if you take the sum over all of them, these two terms cancel out. And now, for example, this term here, rewriting it like this, we see that here we have 1 over this n prime squared, and then we have the sum over all integers n2 cube. So this term will give exactly zeta 2 times psi 3. Because this part here, if I take the sum over all integers n1 of this part here, this will exactly be psi 3. And if I take the sum over all positive integers squared, then I get zeta 2. And also this term here, and this term here, so the first term here gives 2 times zeta 3, and this gives psi 2, and here we have 1 times zeta 3 and psi 2, so this gives exactly in total 3 times zeta 3 times psi 2. So here we see that this multitangent psi 3, 2 can be written as a multi-zeta linear combination of this monotangent function. So here it's 3 times zeta 3 psi 2 plus zeta 2 psi 3. And also the sum here, it starts at 2, because here the term which corresponds to psi 1, this cancels out. Okay, so now what is the connection of these multitangent or these monotangent functions to our Q series G hat? So this is given by the following theorem, or proposition. So the statement is that that for all integers greater or equal to 2, this G hat, K1 up to Kr, can always be written as an ordered sum of these monotangent functions. And maybe put it here. And this is a direct consequence of the Lipschitz formula, because, so proof sketch. So again, the monotangent psi k is exactly the left-hand side of the Lipschitz formula, and therefore we know this equals this guy here. So therefore, if I write this ordered sum here on the right-hand side out, I have this ordered sum m1 up to ml. And now I can, or maybe first, let me put this minus 2 pi I, where for each of these terms I get a factor minus 2 pi I to the k. So here I have minus 2 pi I to the k1 up to kr. And then inside here I have, so I get a sum d1 up to dr greater 0, and here I have dk1 minus 1 over k1 minus 1 factorial up to d1 dr kr minus 1 over kr minus 1 factorial q to the m1 d1 mr dr. And this here is exactly the definition of our Q series small g, gk1 up to kr. I mean, these terms here, taking the sum over these, we could also write by these Eulerian polynomials. Okay, so let me recall. We have these multitangent functions, which can always be written in terms of monotangent functions. So they can always be written in terms of these monotangent functions. And the connection of these monotangent functions to our Q series G is given by the fact that whenever I have an ordered sum of these monotangent functions, where I consider psi k1 of m1 tau up to psi kr of mr tau, then this is exactly our Q series G hat. And these are the main ingredients we need for the calculation of our Fourier expansion. But first, we need to do the following. So recall, in the classical case, we split up the summation into 2 parts. So in the single Eisenstein series case. And now we want to split it up into 2 to the r different parts. So first, here's again the definition of the multiple Eisenstein series. So this was defined by taking an ordered sum, lambda 1 greater lambda 2, and so on. But instead of taking an ordered sum, I can also say I take the sum over all tuples, which are in the set of positive lattice points. And instead of saying that lambda 1 here is the largest, I just say here I take the sum of all these lattice points. And then here, I replace this lambda 2 by this term here, lambda 2 up to lambda r. And then of course this term here will be greater than this term, and so on. So now we have the sum over all tuples, lambda 1 up to lambda r in pr, and p, recall here, p is the union of the set u, the lattice points in the upper half plane, and r, the lattice points on the real axis, so the points up and on the right. So therefore we can consider the different cases where these lambda lambda j's are either in U or in R. So therefore we define for some a's, A1 up to AR, so they are now either the set U or they are the set R. Then we define the G, A1 up to AR of K1 K up to KR. Now the partial sum where lambda 1 is in A1, lambda 2 is in A2, and so on. And therefore, in total, if we take the sum over all possible choices of these a's to be R or U, of these partial sums, we get exactly back our multiple Eisenstein series. Okay, and we want to consider these terms separately, and to calculate the Fourier expansion. But first, one example to make this clear. So what is, for example, G of these a's? So A1 is R, A2 is U. So, but more generally, one can think of that we have G of some word of R and in the letters R and U. So what is this by definition? So by definition, this means that we have the sum where lambda 1 is in R, lambda 2 is in U. Let me write it like this. So lambda 1, lambda 2, lambda R is in R, U, R, R, U over lambda 1 plus lambda 5. Oh, so R is 5 in this case. K1 up to lambda R, lambda 5 to the K5. So here, this point, lambda 1 plus lambda 5, so we see here lambda 5 is in U, so for example it could be this, lambda 4 is in R, lambda 3 is in R, lambda 2 is in U, and lambda 1 is in R. So this point here is the sum of these three lattice points. And so maybe I should write it out here. I mean, what is the second part here? It's lambda 2 plus up to lambda 5, K2. So first of all, this here is the part for K1. And here, this is this point. This is the one for K2. And so on. So here's K3, K4, and K5. So I consider all possible ways of summons of this type here. So K5 needs to be in the upper half plane because this lambda 5 is in U. Then this, and then this next lattice point needs to be on the right of this lattice point because lambda 4 is in R, so it needs to be on the right. And lambda 3 is also in R, and therefore this point here is also on the right of this. Because lambda 2 is in U, this point here is now on top of this point here, so it could be anywhere here, for example there. But then this point again needs to be exactly on the right of this because lambda 1 is in R. So we could rewrite this. So instead of taking this sum, I could say, well, I can take this sum over M1. Maybe let me write this here. So let's say the level here is, this is M1 and this is M2. So by this I mean the vertical positions of these 3 points is M2 and the vertical position of these 2 points are M1. So I could take the sum over M1 is greater than M2 is greater than 0. And for a fixed M1 and M2, I consider here the sum over all points on this level, which can go up to the left and to the right. So here I could say I take the sum over all N3, N4, N5, and also here I have N1 and N2. So here I have the sum over all N1 greater than N2 of these terms, and here I have the sum of n3 greater than n4, n4 greater than n5, but this here will be exactly psi k1, k2, m1 tau, and this here will be exactly psi k3, k4, k5 of m2 tau. Because the definition of this psi is exactly this, that maybe here I can write it out. Here I have m2 tau plus n3 k3, m2 tau plus n4 k4, and here m2 tau plus n5 k5. And this is exactly the definition of psi k3, k4, k5 of m2 tau. And here similar we have this. So in total we have an ordered sum m1, m2 of psi k1, k2, m1 tau, psi k2, k3, k4, k5, m2 tau. So we have an ordered sum of multitangent functions, but then we can use the theorem and say every multitangent function can be written as a finite linear combination of monotangent functions, and then we will have an ordered sum of monotangent functions, or some linear combination of these with multi-zetas as coefficients, and a linear combination of monotangent functions is, by this proposition here, is always our g hat. And this will be the basic idea of calculating the Fourier expansion. But this we will do now explicitly in the depth 1 and depth 2 case. Well, in depth 1 we already did it, but now let's do it with the new notation. So depth 1, there are two cases, so the lattice point could be in R or it could be in U. So if I have the lattice point in R, this just means I take the sum of all lattice points on the positive real axis. So GRK tau. Well, this is just the sum over all lattice points on the positive axis. So this is just n to the k, so this is just theta k. And the lattice points on the, for U, means I take all lattice points on the upper half plane. But again, with the argument as before, we can say, well, I can take the sum over m for all possible positive n, so m is positive, and then for a fixed m, I take the sum in all horizontal directions, so then I have m tau plus n to the k, and this is exactly what we calculated before. This is just g hat of k by using the Lipschitz summation formula. Because here this is a monotangent function, this is psi k of m tau. And an ordered sum of monotangent is g hat. But now, so the fun starts in depth 2. So now we have 4 cases. We always have 2 to the r different cases. And so let's consider first g, k1, k2, r. So I take lattice points here, both of them, so lambda 1 and lambda 2 are both on the positive real axis, so therefore also the sum of these, so here this is the sum of lambda 1 plus lambda 2, and this is just lambda 2, so they will be, if I take the sum over all of them, this will be just the sum over all ordered lattice, all positive natural numbers, and therefore this is just the zeta value, zeta k1, k2, because here, there I have k1 and there I have k2. And now the other simple case is UU. So this is this case here. Maybe I make this smaller. So I have lambda 2, and then lambda 1. So here this is k1 and this is k2. So I take the sum over all pairs like this, but this just means, again, here I can say this is m2 and this is m1. So I take the sum over all m1 greater than m2. And for a fixed m1, I take the sum over all points in this direction, and for a fixed m2, I take the sum over all here. But these are just, again, the monotangent function k psi k1 m1 tau, m psi k2 m2 tau. And this is just by the proposition g hat k1 k2, because this is an ordered sum of monotangent functions. Okay, so now we have this term and this term. Now we come to these terms, so the new terms where we have a mix of u and r. But this term here, if I have a word ending in r, then this is also easy, because what is gur, k1, k2? Well, in this case, lambda 2 is in r. So here I have lambda 2. And then lambda 1 is in u. For example, this one here. And here is k2 and this is k1. But this just means, so they are independent of each other, because I just consider all possible positive points here on the real axis. And then because it takes the sum over all possible lambdas in u, I could go in any direction. So this just means I take the sum over all lattice points in the upper half plane, and here I take the points on the positive real axis, and they are independent. And this term here just gives me the Riemann zeta value, and this just gives me, again, just the sum over all lattice points in the upper half plane. This just gives the g hat. So this here, I can write it again. So this just means I take the sum over all m greater than 0, and n1 can be any integer. So this corresponds to this here. So here is n1. And here I take the n2 here be anything. So this is then m tau plus n1 k1. And here 1 over n2 k2. But this term here just gives the Riemann zeta value, zeta k2. And this part here is just, again, so this is a monotangent function, and then I take an ordered sum, and therefore this is just g hat of k1. Okay, so this term is also quite simple. But now the hardest part is the case when we have a word ending in u. So this means lambda 2 is in u, and then lambda 1 is in r. And here I have k2 and here I have k1. So I need to take the sum over all of these pairs like this. But this just means I can take the sum over all positive m. And for a fixed m, I need to take the sum over all pairs, here with n2 and n1, where n1 is greater than n2, of m tau plus n1 k1, m tau plus n2 k2. So this is m1 is greater than 0, and here this is the definition of the multitangent function in depth 2. So this is psi k1 k2 of m tau. And now we really need to use this theorem of this reduction of multitangent to monotangent. So here we can now use that this multitangent function psi k1 k2 can be written as a linear combination of these monotangent psi j. So this sum here can be written now as a sum j goes from 2 to k1 k2, with some coefficients which are given by multiple zeta values. And here now I have the sum m greater than 0 of psi j of this monotangent at m tau. And this here, now it's again monotangent ordered sum, so this is g hat of j. Okay, so in total we have this thing here. The Fourier expansion of the double Eisenstein series has the double zeta value zeta k1, k2. So this comes from the RR. Maybe I can get it down here. Oops. So here, this gives this. The word ending in R just gives a multiple zeta value here. So this gives this. The UU just gives a sum over an ordered sum over two monotangent functions, which gives a g hat. And this word here ending in U just gives this multitangent, which then can be written as a linear combination of monotangent, which then gives this multi-zeta linear combination of this g hat in depth 1. Okay, so in general, we have the following. So whenever this word here is just r, so now we say that we consider g of some w, where w is now a word in the letters a, l, r, and u, of k1 to kr. So if it's just the word r, so this just means all lattice points are here on the real axis, so this just gives a zeta value. If this is u, then this means I have the case like this, where I have different m's here, and for a fixed m, I just take the sum over all n in this direction, which gives monotangent functions here, and then this just gives a g hat. And if a word ends in r, this means here the last lattice points are on the real axis, and then at some point there's a u, and therefore so from here there's some rest, which I denote here by w prime. So if I have a word w which has some w prime which ends in u, and then there's some r's, then this just means that I can split off these terms here, which gives me a multiple zeta value, and afterwards I have a g of w prime where the last letter is in u. So it's something starting in the upper half plane. And in general, if I have a word ending in u, so this means I have some u, and then maybe some r's, r. Then at some point I again have some u, some r, and so on. And for each of these u, I can take an m, so I get an ordered sum of m's. And for a fixed m, I take the sum over all ordered n's, which then gives a multitangent function. So for each m, I get the multitangent function. And then I use this theorem, which reduces multitangent functions to monotangent functions, and then I get an ordered sum over monotangent functions, which then gives the g hat. And this is the sketch of the proof of the theorem. So let's go back to the statement. So the statement was that every multiple zeta value can be written as a multi-zeta linear combination of g hat. So here the first term is the case r, and the last term is u. And in between we have the mix of r and u. If a word ends in r, we can always split off some multi-zetas, and if it's end in u, then we can use this reduction theorem, which gives a multi-zeta linear combination of monotangent, and then we get a monotangent, an ordered sum over monotangent gives these g hats. And this is how this formula works. And since these coefficients, these cj's in the theorem of this reduction, are quite explicit, one can also give explicit formulas for these alpha j's, but they are quite messy. So here in the end I give an example in depth 2 and depth 3. So for example in depth 2 it's not so messy yet, but So in DEFs2, the Fourier expansion of the Doppel-Eisenstein series, which was first considered by Gange Gonzagi, but also again done in my thesis and the work with Tasaka, we get the constant term and this g hat, and here in between we have a mix of Riemann zeta values and single g's, and the coefficients can be written down explicitly by these binomial coefficients, which comes from this partial fraction decomposition. And in DEF3 you can also do it explicitly, but you see that these formulas get quite messy, but they are explicit. So these binomial coefficients always come from writing down the partial fraction decomposition explicitly, and then you see that here we have these double zeta values and the single g's and all possible mix. And they always have, so for example here you see it's a product of two single zeta values and single g, but these we could for example multiply out using the shuffle product formula, and therefore this would also be a linear combination of DEFs2 multiple zeta values. And yeah, so I want to end this section by the following, by talking about the Stafford product of these multiple Eisenstein series. So we saw in the definition of multiple Eisenstein series that by definition they also satisfy the Stafford product formula. So for example, if I multiply G2 with G3, I could write this as G23 plus G32 plus G5. But of course I can also first write them by their Fourier expansion here, because this is zeta 2 plus g hat 2 and zeta 3 plus g hat 3. So if I multiply this out, I get this expression here. But also I can use now the Fourier expansion of these double Eisenstein series here, so G23 and G32. So here is this example. So if you use the explicit formula from before, you can see that G23 is zeta 23, and then this mix here of the Riemann zeta and a single g and this g hat. So if you plug these two formulas in here, we also get an equality that this equals this. So in the end we get some expression for the product of these g hats, which is exactly given by this here. So first notice, if you look at the constant term of these guys and also G5, then this is just the Stafford product for the zeta values. And from the rest you see that you get that this product here can be written as G32 plus G23 plus G5. So this somehow corresponds to the Stafford product, but we also have this extra term here 2 times zeta 2. And now if you divide by minus 2 pi I to the power 5, what we get is this formula here. So g hat was just given by this power of pi times the q series g. So if we do this here, if we divide out this, then here minus 2 pi I to the cube sends this to G3, and zeta 2 can be written as, well, if you divide out minus 2 pi I squared, then we get minus 1 over 12. And this formula we already saw before when we considered the Stafford product formula, or the quasi-shuffle product for this small g. So in other words, we could use this here to prove this equality, and then show that the double Eisenstein series actually satisfy the Stafford product without using this definition as ordered lattice sums. So here's some nice connection between these two Stafford products of this G and these multiple Eisenstein series. But you could also think it like this. So these small g, they do not really satisfy the Stafford product because there's an extra term. So therefore, in some sense, these multiple Eisenstein series are a nice linear combination of these g hat with multi-zetas, such that they really satisfy the exact Stafford product without these extra terms, because these extra terms are now inside the definition of these double Eisenstein series. Okay, so and next time we will talk about regularized multiple Eisenstein series. So in our case here, these indices, they needed to be greater or equal to 2. So if we go back to the definition of multiple Eisenstein series, here we had this restriction here that everything needs to be greater or equal to 2, where for absolute convergence then first needed to be greater or equal to 3, but then we could use Eisenstein summation. And then today we saw that they can be written as some zeta k1 up to kr plus some Fourier expansion, where a, n are given by some multiple zeta values. And the natural question is if we can extend maybe this definition here, such that we still have this Fourier expansion where the constant term is exactly the multiple zeta value. And then the question is, what is a good definition and what is then the Fourier expansion here? And there are two ways to do this. So there's a shuffle regularized version due to me and Tasaka, and also there's stuffle regularized version. And next time we will introduce this shuffle regularized multiple zeta value, the shuffle regularized multiple Eisenstein series, and its connection to the so-called Gonchorov coproduct. Or more precisely, we will see that this construction we did today corresponds in some sense to the calculation of a certain coproduct on the space of formal iterated integrals. See you then.